Okay, time to get started. Welcome, everybody. Thanks for making it on a Monday of Thanksgiving week. Appreciate your attendance. Just picking up where we were last time, we were talking about light bulbs. Okay? I think these are lovely physical examples for what divergence looks like and what the divergence theorem does for us. And so just hitting the highlights from last time, the punchline was that if you look at where the divergence is huge, the divergence is huge exactly at the source of the light. Right? Then keep in mind, the source of the light, that's where the boundary flux ultimately comes from. Right? Now, yeah, we measure it on the boundary. And I talked about this a lot, about how just because you measure it on the boundary doesn't mean it actually comes from or originates on the boundary. And case in point, right? Of course there's a tremendous amount of flux through the boundary. Is that where the light's coming from? No, obviously not. It's coming from the little LED at the middle of the light bulb. Right? That's where it's coming from. Divergence is pointing to where the boundary flux that we measure is actually coming from. And now what about other points, right? If I were to look, like right there, and if I think about, how much of the flux that I'm measuring on the boundary is coming from inside some little vicinity, let's say right there where there's no light bulb, right? Well, again, let's just think through the mechanics of what's going on here. Are there any photons that are originating in there? No. And divergence, again, points to that perfectly. Right? Another way to think about it, and again, I think this is a really useful little observation to make. Sure, there's a lot of photons in this little region here, this little green ball here, right? But they're all passing through. Right? Every photon that goes in goes out. Every photon contributes both to the negative flux, the negative outward-oriented boundary flux, as it goes into the region, and then contributes positively in exactly the same amount as it leaves that little region. So passing through only doesn't contribute at all to the actual flux. Yeah?
I'm a little confused. If the field lines are getting smaller,
yeah.
Yes. The arrows are getting smaller.
Yes.
Does that mean that there is divergence?
You would kind of think so. But yeah, it doesn't. Yes, they are getting smaller, but they're also kind of spreading out. And so if you wanted to get real tight on one of these little circles, right? There are exits happening over a greater portion of that boundary sphere than there are entrances, and that ends up being an exactly balancing force, as it turns out. Yeah, and again, if you don't believe me, take this formula for the vector field and compute its divergence, and you get zero. It's just, it is. Yeah, a little counterintuitive, absolutely. Okay, so that was the example we ended with last time. Now, I will point out there is something about this example, very specific feature. Oh, by the way, I should confess one thing. I did change some of the stuff on this page of notes. Forgot to mention. It's going to end up being useful for me to have this little comment right here. This is just the observation that the flow of light is an inverse square radial vector field. So I'm going to call back to that in a bit. So I did add that to the notes. The new copy of the notes is posted on the class website in the class materials folder. Okay, yeah, so there's some specifics about this example I want to point out. The fluid is being generated. Right? But photon density, fluid density, is constant over time. So we're not seeing, the nature of this flow is not that there's a finite amount of fluid and it's moving around and less of it results because it moved, right? It's a totally different kind of fluid. The actual photon density, the actual fluid density is time independent. And the flow we're seeing because we're seeing literally a generation of fluid. Now that's in contrast to this next example. In this next example, the idea here is that I have a certain amount of gas in the general vicinity of this large sphere. And I'm going to imagine that the temperature starts to rise. And if you don't know the the physics of gases and relationship to temperature. As it turns out, when you raise the temperature, the gas will tend to expand. And so the resulting flow, as the gas expands, there's sort of an resulting outward flow of the gas. And this is what the vector field ends up being. This right here, outward flow of gas. And now I claim that the flow is shorter vectors closer to the origin, because if you think about it, at the origin, that's the point everything is emanating outward from, right? So that the gas there doesn't move in any direction. It's kind of, in some sense, the opposite of, what's happening on this side versus, what's happening on that side. It's sort of the balance in between. So that point actually doesn't move at all. Again, another flow of a fluid, but in a very different way, right? With the light bulb example, we're generating fluid, but density is a constant. Here, we're not generating any fluid at all. Totally different physical scenario. But the density is changing. It is not constant, right? Because again, the gas is expanding, and if you have a finite amount of gas, as it expands, the density goes down. Okay, so different physical scenario. And so we're going to make a different interpretation then of the flux. And let's just think about, let's look at the sphere here. On that sphere, again, there's clearly a flux. As the gas expands, some of that gas is going to be flowing through this boundary sphere. Right? And I can, as per usual, I can interpret that flux in one way by, let's just write down the divergence theorem. So here we go, no big deal. Divergence theorem says flux is an integral of divergence. And by the way, you can totally compute this divergent, wrong color. You can totally compute the divergence here. Ends up being 3K. Good little exercise. Make sure you can do this. The tricky little bit on this is that I've given you the vector field in a vector form, but I've given you the formula for divergence several pages back in coordinate form. So you just need to rewrite this vector field by coordinates and then just plug into the formula. Okay, make sure you can do that. Okay, so what's the interpretation here, right? Is divergence here pointing to where the fluid is being created, like here, right? We agreed that the divergence is pointing to where the photons are being created, because that's the nature of this fluid, as it turns out. Right? But of course, it can't be this interpretation for this example. In this example, nothing's being created. There's a finite amount of gas. We're not generating gas here, right? So what interpretation will we take? What does this 3K mean? What does that value, which by the way is a constant, right? What does that constant value tell us? And the way I like to do this, by the way, this is another change that I've made to these notes just today, earlier this morning. And that is to make the observation that in this case, flux represents fluid leaving the region and therefore represents the rate of decrease of the total amount of fluid in that region. Right, now this is just a geometric sort of physical appeal. As fluid leaves, right, the grand total amount of fluid in there is decreasing. Right? More flux, faster rate of decrease of the quantity of fluid inside of that sphere. And by the way, note the minus sign here. Minus indicating that the flux is giving you the negative of the rate of increase because it's giving you the rate of decrease. Okay. So, having made that observation, a little bit of math here, no big deal, but of course mass is an integral of density. Here, let me zoom. We can see better. Whoops. Come on. There we go. Too much. Hang on. There we go. Okay, mass is an integral of density. Write that down. And now let's observe that I can pass this time derivative in here and apply it to the density, like so. And nice punchline then, if I can get this to cooperate again. Nice punchline is that we get ourselves an interpretation of what the divergence means. This divergence that I computed as 3K, right? What that is, as I've indicated here, it's telling you how fast is the density decreasing at any given point. And again, if we got this integral and going all the way around is equal to this integral. You have two integrals that are equal. That means their integrands have to equal. So divergence, apparently, the rate of decrease of density of gas wherever you might be computing it. And so the interpretation then is that this vector field representing this expansion of gas, in the process of following this vector field as the gas expands, the rate that the density is going down is the same everywhere inside of the ball. Yes?
So is the reason why you can put the derivative inside the integrand, that's because the volume is constant?
It's because of what now?
Because the volume is constant?
Yeah. That's right. Yeah, absolutely. Yep. Totally. Yeah. There's some sticky wickets that I'm sweeping under the rug here, but yeah, the fact that this region is fixed is an important part of that story. Yeah, right, absolutely. Okay. So the big point to all of this is when you have a different physical scenario, you make a different interpretation of divergence. You have to tailor your interpretation of divergence to the actual situation. It is not always the case that divergence always represents a rate of change of density. Sometimes there is no rate of change of density. Sometimes the divergence represents where the source is that the fluid is coming from. So heads up on this. This was terribly confusing to me when I first started learning this stuff. Let's not count the decades ago. And I finally realized, I finally made this realization that, the reason you get different interpretations is because you have different kinds of fluid. And so, of course, you should have different interpretations. Very quickly, this is really not anything we're going to worry about in any serious sense, but you can generalize to scenarios where you might have both. You might have fluid being generated, and at the same time, you might have density also changing. Ooh, okay, so neither of our previous examples would qualify as such. And how would you deal with this? And here's my take on it. Look, however much fluid is being generated, whatever the rate is that you're generating fluid, if you think about it, there's really only two possibilities for what that new fluid, as you generate fluid, any little piece of that fluid can only do two things. It can either stay in your region, in which case we're contributing to how fast the quantity is increasing, or it can not stay in your region, in which case it leaves the region through the boundary, in which case it contributes to the flux. Right? So this is, if you want to combine both of these scenarios where you have a generation rate and a rate of change of density, right? This equation shows how flux relates to those things. And of course, now again, you have to tailor, what else do you use to interpret flux in this context? Well, if you know the flux and if you know one or the other of these things, then you can solve for the other. Right? Okay. All right. So again, not really what this course is about. This is just for your consideration. You might find this useful in future engineering classes, fluid dynamics, something like that. Okay. Let's talk about gravity. Here's the formula for the gravitational field created by a point mass, which is a bunch of nonsense, by the way. There isn't really any such thing as an actual point mass. This is a mathematical simplification, right. Okay. Inverse square radial. And notice, so was this one. Inverse square radial. That's cool. Very convenient. That the vector field of light bulbs generating photons is morally equivalent to the vector field for gravity. And so here is a take you kind of could. This is a speculation that you could make based on this observation. And as y'all know, I like the little quip: if it looks like a duck, it quacks like a duck, right? This kind of makes it look like the nature of gravity might be that mass is kind of like light bulbs. That mass, in the same way that light bulbs shoot out photons, maybe mass shoots out these little particles that communicate gravitational force. And they speculate these particles being called gravitons. Right? I mean, if mass generates a vector field for the gravitational force that is exactly like a light bulb, maybe mass actually behaves like a light bulb. So now, again, this looks like a duck, quacks like a duck, does not mean it's a duck. It means it behaves like a duck, and you can treat it like a duck. And it's a useful metaphor, and feel free to think of it that way, even if it isn't true. And I am not going to take a position on the question of whether gravitons are real. That's not my domain. That's physicists' problem. My bet, based on what I've heard, and I'm not an expert in this area, but based on what I've heard, if I were a gambling sort, I think I'd be betting against. I probably think they probably don't exist. Right? But again, it doesn't matter. It doesn't matter. The gravitational force, gravitational field, is exactly what it would be if gravitons were real, if mass did actually just emit little particles just like light bulbs do. Right? So for the purposes of what we're doing here, I encourage thinking of it that way. Because, again, it'll lead you entirely to right answers. So here's a really powerful conclusion you can get from this. And let's look at this little square of equations. I guess maybe I'd better not zoom too aggressively here. This top equation is actually an easy one. I know it looks weird. It looks weird because there's this constant on both sides that makes it look a little surprising. But notice, other than those constants, same constants on both sides, it just says mass is an integral of density dV. That's all. This top equation is no problem. An easy one. We'll talk in a moment about where that negative, why am I inserting that negative 4 pi g. But as to whether this equation is true, mass is an integral of density, well, of course it is. Okay, next observation. Let's look at this equation. And why does this kind of track? And the idea is to make a graviton argument. You see, in the top equation we have mass. And let me just remind you, we're playing like, we're doing a little make-believe here. We're pretending that mass generates this fluid called gravitons. And more mass, more gravitons. Right? Now, reasonable question, okay, we've got the mass inside of this region. How much of that fluid, how many of those gravitons will then subsequently leave your region? And all of them do, right? We're not collecting gravitons. The whole idea is that gravitons shoot out and that's what communicates the gravitational field. So more mass makes more gravitons, which makes more flux through the boundary. And so the argument that I've just made shows that these should be proportional. And you can do physics arguments to argue, and I don't want to do that here. Again, that's somebody else's problem. But it turns out the constant of proportionality is negative 4 pi g. That's just, think of that as just, that's just the way it is. Don't worry about the why. Okay, so if you're willing to believe that, right? Well, I have that this equation is true and that equation is true, and wait a minute, flux obeys Gauss's divergence theorem, so we write that down, and notice that we again have ourselves in this kind of interesting situation. Roundabout, I've showed that these two integrals are the same. They're integrals over the same region, and that means that they must have the same integrand, right? And so we get a really nice interpretation then of what divergence of the gravitational field represents. The divergence of the gravitational field apparently is proportional to mass density. More density, more divergence of the gravitational field. So, neat fact. By the way, if you were to try to prove this without clever arguments using the Gauss's divergence theorem, this is a monster. Absolute monster to prove, because you got to notice I was not making any assumptions. In this argument right here, I was not making any assumptions about where the mass is. Right? The mass can be distributed through the interior, whatever way. Who cares? Doesn't matter. Wherever the mass is shooting out gravitons, and more gravitons means more flux. Simple as that. Anywhere within the region. So imagine how hard it would be to write down the actual gravitational field. Yikes. It'd be a monster. Unthinkable. And then I've got to compute various derivatives of that. This would be a terrible, terrible monster, right? So this little crutch of thinking of gravity as communicated by gravitons combined with the divergence theorem gives us a bonkers, simple, powerful conclusion that would have been basically impractical to achieve otherwise. And so really awesome application of the divergence theorem. Everybody buying it? Okay. All right. So, who cares? Right? Very often the case. There are some arguments that don't apply to your specific future, at least not directly. Unless you're going to be an astronaut, the gravitational field is pretty much constant at the surface of the Earth. Do we really need sophisticated takes on the non-trivial cases of what gravitational fields can look like? Again, on the surface of the Earth, gravity's constant, down, nothing to it. Why should you care about this? Not, the non-future astronauts in the class. And the reason why is that this is the perfect metaphor for electric fields. Electric fields and gravitational fields are both inverse square radial. And that means that they behave exactly the same way, except for constants and interpretations and stuff. But the math of electric fields is down to everything but a constant, exactly the same. So you can write down all the same sort of analogous equations, and starting with the innocent observation that charge is an integral of charge density with respect to volume. Make that one observation, and again, cite the divergence theorem, and you get a really, really useful observation about the relationship between the electric field and how charge is distributed. And this is called Maxwell's first equations, the differential form of Maxwell's first equation. Why am I zoomed out? Let me zoom back in. There we go. Side note, taking the integral of both sides of that, as I have here, gives us, I'm going to say morally equivalent sort of version. This is called the integral form of Maxwell's first equation. And they say, again, kind of the same thing. Now, at a glance, at casual glance, if you just look at, this one says it's about flux and charge. This says it's about divergence and density. They don't sound like they're related. Right? but they are. One of the equation on the left is just an integral of the equation on the right. Mathematically, they're really closely connected. And again, the thing that makes that connection, the thing that connects me from the right side of these equations to the left side, the divergence theorem, is what makes that connection. So, bonkers powerful interpretation, application of Gauss's divergence theorem. Super important. When you're studying E&M, really important to understand how the divergence theorem relates these two different forms of Maxwell's equations. And by the way, there are 4 Maxwell's equations. We're going to talk about, let me think here, I'm going to talk about 2 of the 4 because they're such perfect physical manifestations of the divergence theorem. And so this is just one of 2. We'll get to the other one later, maybe not today. We'll see. But yeah. Okay, so summarizing. Electric fields. Y'all, all the engineers in the room are going to have very good intuition for electric fields. And what's the best way to think about electric fields? My personal opinion, the best way to think about them is as being analogous to gravitational fields, because gravitational fields are relatable, right? We've understood gravity we've understood that there is gravity. We have understood the notion of physical mass, right, since prehistoric times. The fact that there is mass, the fact that gravity pulls me down, the relationship between them maybe we didn't get, right? But the objects in play here are all highly relatable, right? Whereas the objects in play here, mysterious, right? Electric charge was not understood. No one had the slightest idea what that was for a very long time. No one had the slightest idea that there was something called an electric field until, a couple hundred years ago? Very recently, if you think about it, right? So this is hard to relate to. The fact that it is mathematically, morally equivalent to something that's easy to relate to, I think is very valuable. And what's the best way to think about gravitational fields? Light bulbs. Again, that's just my opinion, right? But this is the picture that I have in my mind when I'm thinking about gravitational fields and this kind of context. Yeah. Okay. Last little observation I want to make is going back to these 2 equations, and again, cosmetically they don't necessarily look like they have much to do with each other. But let me pronounce these 2 theorems, or these 2 equations, a little bit differently. This is a relationship between flux and charge. This is a relationship between flux density and charge density. This is just, the one on the right is just density version of the one on the left. So another reason that I am a huge fan of understanding divergence as flux density, because it makes Maxwell's equations just roll off the tongue. Borderline obvious, right, if you say it the right way. Okay. All right, so I hope those ideas will be useful to y'all as you proceed through engineering. They certainly were to me in physics. Okay, moving along. Stokes' theorem. Still in section 7.3, right? This massive, gigantic, overpacked section. This theorem is kind of just another example of arguments we've made several times, just different context. We're going to identify a certain accumulating quantity. We're going to argue that it has physical location. It behaves like stuff. It's not actually stuff, but it behaves like stuff, so you can treat it like stuff. And therefore that it has an associated density, and quantities are integrals of density, and we're going to write that all down, and out comes a theorem, another theorem. In the same way that boundary flux, being an accumulating quantity, gave us the divergence theorem, we're about to see a new accumulating quantity whose, following this line of reasoning will result in what's called Stokes' curl theorem. So in order to do so, I've got to talk about boundaries again. Recall, boundary, loaded word. Right? This does not just mean the set of points. Right? This is very specifically an oriented thing, and the orientation is really, really important. So when you have, for example, some surface, like so, and specifically when I say surface, I mean an oriented surface. And remember the way we orient a surface, if you have a surface, something like this, right? A surface. An orientation on a surface, when you're talking about flux integrals, an orientation means a choice of unit normal vector. Right? So notice that's what I have here on the screen. We've got some surface here, and what I call the orientation of the surface is indicated by this unit normal vector. Okay. All right. So the boundary, if you think about it, the boundary of a piece of surface is going to be a curve. Right? That's the sort of where the surface ends. If you will, my silly little metaphor for how the surface ending is that imagine there's an ant crawling around. Ants are so lightweight they basically don't even notice gravity, right? So they don't notice if the surface goes upside down. Couldn't care less, right? Whatever. They're just walking around, and yet at some point they're going to get really confused, right? Nothing weird happens when the surface goes vertical. Nothing weird happens to the ant when the surface goes upside down. But when they get to the edge, they're like, whoa, the universe just ended. I reached the end of space, right? They get super confused. Right? So that's the way I like to think of boundary. What do we mean when we say boundary of a surface? Where does the ant get confused? Okay. And this boundary also needs to be oriented. So the boundary curve comes with an orientation, and its orientation is according to a very specific rule. And again, there's several different ways that you can state this rule. And I think a pretty good one is to use what I'm going to call the right-hand rule. There's various different versions of right-hand rule. I think this is the easiest way to think of this. What you do, if you're looking at a piece of the boundary curve, and if you want to know which of the two possible tangent directions, which way should you go, what's the correct direction around that boundary, pick a point near, not on, but near the boundary. Look at the normal vector there. Point your thumb of your right hand in the direction of that surface orientation unit normal. Notice that with the thumb of your right hand pointed in that direction, your fingers of your right hand will point around, and thus creating what I like to call a swirl. Let me draw a little picture of this. The swirl, you know what? Let me do this in the pencil. I'm going to need a little bit more detail. The swirl is an indication of which direction around that surface, that normal vector. And this swirl, just think about how does that swirl sideswipe up against the boundary. And in this case, if you just imagine this purple swirl going like this, as that swirl sort of side swipes against the boundary, notice it's going that way. And that's our indication that this is the correct orientation of the, and you got to be careful about this, of the boundary, and boundaries are oriented. So when we say the boundary curve, that is again an oriented thing, and it's oriented according to that rule. Arbitrary rule. Why the right hand? Why not the left hand? It's just that's just a convention. It's an arbitrary standard that got picked long ago. Okay. Everybody see what the rule is? Questions? Everybody's happy? All right. Well, example number 6. I've lost count, right? But we've seen the following many, many times. we have an accumulating quantity. Here, I claim that boundary circulation, so for example, if I look at boundary circulation around the left piece, and if I look at boundary circulation around the right piece, and again, paying attention to the orientations, following the rule that we just discussed, right? That boundary circulation of the left plus the boundary circulation of the right leads to a cancellation, which again we've seen several times laid out on the page to conjure all those memories. These interior pieces, same edge, opposite orientations, they cancel, and as a result, we get the boundary circulation of the whole. So what we have then, boundary circulation is an accumulating quantity. Now, the argument here is geometrically a little bit different, but awfully reminiscent of an argument we made about Green's theorem, of an argument we made about Gauss's divergence theorem, of an argument we made about the two-dimensional divergence theorem. Arguably kind of not that different from an argument we made about the fundamental theorem of line integrals, the fundamental theorem of calculus, so I lost count again. Anyway, I think that we've seen stuff like this several times, right? So we have an accumulating quantity, and remember, we have established that when you find an accumulating quantity, you can argue that it behaves like stuff. Physically, it isn't stuff, but it behaves like stuff, so we're going to treat it like stuff, and it won't lead us astray. There's an associated density we can compute. Now, the details of where this comes from are, I feel at this stage anyway, a distraction from the point. The point is circulation density. So circulation per unit area. Keeping in mind, circulation computed on the boundary, like so. Per unit area. That's the area of what that boundary sort of goes around on our surface. Is something we can discuss, right? Again, circulation's a kind of a stuff. It behaves like stuff. We're going to treat it like stuff. We can talk about stuff per unit size. And there is a formula for it. Circulation density is this right here. It's curl dot orientation unit normal. That's the formula. And there's some really nice geometry to make sense out of this. You know, what does this look like, and how does this help me understand what curl looks like? Right. Ultimately, one of our big goals here is to figure out what does curl mean, and how do I relate to it? What will curl tell me? Right. We'll make those interpretations in a bit. For the moment, I just want to kind of put it all together and write down a theorem and do an example, and let's cross the finish line and put one in the win column, and then we'll come back and make interpretations. So again, a quick reminder: we have an accumulating quantity. It behaves like stuff. Has an associated stuff per unit size. And then we put it all together. So putting it all together, let's see here, color choices. Circulation is the quantity in question. We argued that it's an accumulating quantity. We've done this a million times, so I'm going quickly. Any little piece of that stuff can be thought of as stuff per unit size times size. So there's this density idea, right? Stuff per unit size is density. And again, I'm claiming that this is the formula. And so arguably we have kind of a theorem. And again, notice that the way I write these theorems down, it's all ripping. I'm stealing from previous examples in which I was stealing from previous examples. All of these theorems we're seeing sort of from the same approach. And you can say right off the bat then, okay, well then there's our theorem. And you can write it down like this, and in a lot of books they do, and there's nothing wrong with that. It's perfectly fine to write it down this way. I just like making the observation that seemingly in a lucky coincidence, we have in DS. It came up coincidentally. I was not thinking of this as a flux argument, right? I was thinking about literally adding up scalar quantities of circulation, adding up over a surface. I was expecting this to turn, as it kind of at a glance appeared to have, as a scalar surface integral, but the density just happens to have a dot in it, and in ds is our ds vector. And so weird opportunity arises. We can reinterpret this, I think, as we should, as being not a scalar surface integral, as a vector surface integral. And I like to write it like this. I think it's more natural to write it like this. Yeah.
What's the difference between Stokes' theorem and Green's theorem?
Yeah, it's a great question. They have a lot in common. They're both about circulation, right? They both say that circulation is an integral of circulation density, appropriate to the context. The context is the difference. Green's theorem is strictly in 2 dimensions. So 2-dimensional vector fields and curves in a 2-dimensional, like an XY plane, something like that. Stokes' theorem is 3-dimensional, and so the vector field's 3-dimensional, the surface is in 3 dimensions, etc. Yeah, it's a great question. Okay. All right, so new theorem. Let's use it. I gotta tailor the thing here. Apparently we want to compute a line integral. And as usual, the vector field is given, and the curve is given. By the way, notice that this is not just a random curve. This is an oriented curve. Heads up point for your consideration. Sometimes the orientations are given in subtle ways. Sometimes it will just come out and say it. Oriented, it'll explicitly tell you how the orientation is, and it'll even say the word orientation. Here it's subtle, but notice it was that the curve is given parametrized. When a curve is given parametrized, keep in mind the parametrization has an orientation. So when you write down a parametrization, you are implying an orientation, namely the orientation that, which direction is this parametrization actually going around the curve. Is everybody cool with that? Does that make sense? Okay. All right. So we have an oriented curve, and we want to compute the line integral. Now, is this curve a boundary? We got to be careful about this. Remember, orientations matter. This curve, if you think it through, by the way, if you want, you can take a derivative, right, and literally compute the velocity vector and put that onto the picture and explicitly see which direction that velocity points, and that will tell you the orientation. I like this other point of view, which is that this is a reflection over the x-axis of what I'll call the usual cosine t, sine t, unit circle in the xy plane. And so because it's a reflection of that means that this is actually that. Different point of view. You may recall we made an argument like this back in chapter 6 at some point. So either of those arguments you prefer. Okay, so here's our curve then. Our curve is, let's see here, well, it's the unit circle oriented as indicated. Now we just have to ask, is that a boundary? Now, a lot of students make a mistake here. Common mistake is to think, oh, no, that's not a boundary because it's going the wrong way. And I'll say this, it's not a boundary of what you might kind of expect. I mean, when you look at this picture, we tend to think in terms of looking at let's say this disc like this, and we tend to think of the orientation as being up, but you don't have to. Right? We're making up the surface. We can orient the surface however we like. And I'm going to say, let's orient it downward, like so. And now, let's play the game, the usual game. Right? Is this a boundary? And I don't like here how my okay, let me just do that again. I was slightly bugged by the discontinuity there. Let's play the game. Let's think about this green surface. Keep in mind, it's my surface. I made it up. I can make it however I want. I wanted to orient it downward and thumb in the direction of the surface normal. Thumb downward. Right hand. It's got to be your right hand. Look at the way the fingers are going. My fingers make a swirl. Let's see here. Put this right here. My swirl goes kind of around like that. And you think about how that side swipes on the surface. And sure enough, it side swipes in the direction that it's supposed to, right? The actual orientation that was given is as indicated in dark blue. And the induced orientation from this boundary of this green surface I made up, also same direction. So it's a boundary. Everybody buying it? Okay. All right. Well, we're in business. Let's see here. I will do that. Okay. So being as it is a boundary, I can write down Stokes' theorem. And again, our curve, our domain here, that curve oriented like so is a boundary. Having observed that it's a boundary, I can apply Stokes' theorem. There's Stokes' theorem. And plug and chug at this point. Now, there's a couple of little convenient freebies. One is, keep in mind, I've already established for my surface, I've already established exactly what my orientation unit normal is. So this is just 0, 0, 1. The curl, how do I compute the curl here? Well, okay, compute the curl. I'm going to have to take my vector field. I'm going to have to plug into the formula for curl. This is a formula that goes back to Chapter 3, right? So you do have to make sure that you remember that formula from Chapter 3. Make sure you can execute that formula. There's various partial derivatives, etc. It's plug and chug. Y'all can totally do that part. And the curl ends up being 0, 0, 2. And so instead of dealing with this not very pretty vector field and computing the circulation manually, you might say, I can instead capitalize on the fact that this dot product works out really nicely. Ultimately, I'm just computing an integral on this surface on the unit disk, right? Easy surface, easy integrand, and simple geometry argument. Tells me what the flux is that I was interested in the first place. And the flux ends up being minus 2 pi. No nasty computations required. How we doing? Everybody all right? Okay. All right, let's see here. Are we at, well, we're pretty close to out of time. Yeah, okay, I'm going to give you all 40 seconds. I'm sure I owe you more than that. I'll draw the line right here. Thanks for coming in. Hope you all have a good Thanksgiving break. See you on a week from today. All right, have a good one. And don't forget about attendance if I didn't already get you.